Okay, good afternoon or good morning to everybody attending today from wherever you are based today. Thank you for joining us on this next installment of our series of webinars. This is our fifth one in the suite of ultrasound discussions that we've been having. Today, we're going to be covering energy conservation part 2. Following on from last webinar on leak inspection, today we are looking at improving our steam system efficiency. Just a few housekeeping rules. This webinar is being recorded. It will be uploaded later on to our YouTube channel, and you will be able to watch this over and over again. If you have any questions, please feel free to type them in on the chat group. I will hopefully, if I have time to answer them during the webinar, I will. But if I do not have time, I will then get an answer to your question after this webinar as well. So this is live, so if there's any technical problems, please bear with us, but we'll start and we'll begin. So my name is Chris Hallum. I am the UK and Ireland manager for UE Systems Europe. My contact details are up on the display now for any questions or any requests or anything you need in the future. It'll also be up at the end of the presentation as well for you to make a note if you need to. So a little bit again about UE Systems and who we are. Founded in 1973, we're a manufacturer of airborne and ultrasound, airborne structure-borne ultrasound instruments, along with software, sensors, and training. We're not a service provider. We are a manufacturer of equipment that enable you, the users, the ability to be self-sufficient. Our main headquarters is in New York in the US. But we also have regional headquarters based on all of the continents as well. We come under the European headquarters in the Netherlands as part of UE Systems Europe. And within UE Systems Europe, we have representation in the UK and Ireland, Germany, France, Spain, Poland, Italy, and Eastern Europe. So let's set the bigger picture for today's webinar. So steam is a widely used commodity by many industries, from pharmaceuticals to food to energy generation to food processing. There's many applications and industries that use steam for many different things, from heating to cleaning, moisturization, sterilization. Gets lots of different uses from steam itself. So now, no matter the way that a boiler or steam system is fueled, a large amount of energy is required to generate the steam. And having an efficient steam system will also optimize our plant's energy consumption. With a heating process, there's always going to be a fight on its hands with cooling variables, wanting to cool the system down and use that energy to keep the heat at its optimal level. That's why we have specific assets in place around our steam system to help remove this cooling process, in turn keeping our system efficiency up. Now, operating costs can increase by as much as 33% if there are faulty components within the system as well. So we need to keep on top of those and look at how we can keep on top of those to keep our efficiency at its optimal level. So what does exist out there within the system itself to help steam systems efficiency? And we look here in this webinar at the humble steam trap. Lovely little thing. The steam system will consist of many different types of these traps, depending on the amount of steam being processed, the use of it, and how it's being used. Now, the operation of the trap will affect the system's efficiency. And we're going to go over a little bit further about that as we go through this. But what is a steam trap and what is its purpose in life? Now, I appreciate that some of you would have a lot of experience and knowledge in this field, but I'm just going to go over some basic concepts behind it and how it works and why we have it there, and how we then go on to inspect it and understand the condition of these systems. So first of all, yes, steam is the clear gas. Once we start seeing, say for example, leaks, we start seeing plumes of what people sometimes call steam. It's the vapor phase. That's the condensate. It's the liquid form. If we have that cooled liquid in a steam system, we're going to then start speeding up the cooling process of the steam. So we need to have that removed. And if we have liquid in a high pressure system, we're also going to get problems like water hammer. So the steam trap itself is designed and implemented into a steam system to help us with venting unwanted air and gases, removing our condensate from the system, but holding back the steam. That way we can keep the heat and the optimal temperature at its best, hopefully improving our energy consumption. If we have faulty traps within the system, it's going to reduce our system of energy efficiency because it's going to just speed up that cooling effect again, putting more pressure on the boiler to keep that temperature up. So how does ultrasound detect a condition of a steam trap? So steam systems operate under high pressures, and with our steam traps, they operate like a modulating valve, opening and closing, removing the condensate, holding back the steam. And by doing that, as a medium travels through as the medium travels through the trap or valve, it generates turbulence. And as we know from previous webinars and discussions, turbulence generates ultrasound. And we can use the structure-borne ultrasound inspection method with our probes at 25 kilohertz, for example, and we can listen for the modulation of the trap or also for any leakage that we may hear. So we have two types of operation when it comes to the steam traps. The first being a continuous flow type trap that will allow a continuous flow of condensate, normally in areas where we have a higher buildup. And then we also have the on-off type trap that will open and close as we get a buildup of condensate. And we'll go into the different types a bit further as we go along. So what do we do and how do we inspect? So what we will do is, if our probe has the ability to frequency tune, we will tune our frequency centered on 25 kilohertz. And we will also have the steam application selected within the settings of our probe. If we have a probe that is not so sophisticated, that is a fixed frequency, we can still listen to the trap. It might just be that the sound quality might not be as accurate or as detailed as it would be if you could tune it to 25 kilohertz. What we would do first of all is, using the contact probe, is we would then touch upstream of the steam trap first of all to get a level of the sound, reducing our sensitivity to make it audibly for us sensible and not too loud. And then what we can do from there is then touch the outlet of the trap and listen for the turbulence as it cycles, because where we're going to get the turbulence is at the outlet of the trap. So we can listen for it opening and closing, or we can also listen to the continuous flow. And while we're doing that, if we also have the ability to do, we can perform sound recordings. So we can compare like for like, which is always useful when performing this for the first time round. So if we're not sure about something, we can then compare it with multiple traps that are like for like. So let's start going into a few of the different types of traps and how they operate, so we can get an understanding of how they operate and what they should sound like. So the first one we have is the inverted bucket trap. It's a on-off type of trap, so opening and closing. As the steam turns to condensate within the bucket will drop. That then opening up the valve to allow the condensate to be flushed through. As it's flushed through and steam returns into the bucket will then float back up, closing the trap. I have a sound which I will play now that is an example of a inverted bucket trap. So as you can hear from that sound, we can hear turbulence increasing and decreasing as it opens and closes. So we can hear a clear cycling of the trap. Another way of indicating a condition of a trap could be through thermal imaging, for example, because for a trap that's operating correctly, the outlet should be cooler than the inlet, because all we're allowing out of the outlet is condensate, which will be cooler than the steam. But that only gives us one part of the picture. That would not tell us that it could be blocked, for example. So we have the ultrasound there to give us the bigger picture. Now, here is an example of a failed inverted bucket trap. As we can hear from that sound file, there is almost like a constant flow of turbulence. And when a steam trap does fail, it usually fails in the open position. So we get a constant blow through of steam. And from this, we can hear no modulation. We can maybe hear some mechanical sounds there because there are mechanical components within the trap that could be faulty, that are causing this problem of not being able to cycle correctly. So another example of the inverted bucket, good versus bad. I'll just play these sound files so as a comparison again. So as you can see from the time waveform recording there, we can see that turbulence increasing and then decreasing. And when it decreases, we can see it's closed. And because the amplitude of the sound stays low, we know that the trap is working correctly and it's not leaking also. So we could even identify with a sound recording if a trap is working correctly with maybe some leakage occurring. So here we can see it's operating correctly. Another one that's not so good. As we can hear from that sound recording there, we're hearing a lot of mechanical sounds, a lot of rattling around inside the body of the steam trap there. And that's going to be down to, like I was saying earlier, the mechanical components within the trap itself being faulty. As long as we understand what type of trap we're inspecting, we can start to understand how it should sound. And this is a good comparison with being able to say that this trap is not working correctly. So one of the next ones is the thermostatic steam trap. This is another on-off type trap that operates through temperature changes. As the system heats up, we'll see the bellows actually closing the trap off. As a buildup of condensate occurs around the bellows, they will allow them to open up, flushing out the condensate, and as the steam returns, it'll start to close it again. Now, with these traps, we don't want to inspect them until the system is at full temperature. On startup, these traps are not going to work correctly until we're at temperature. So, an example of a good thermostatic trap. So from the sound file there, we can hear the turbulence increasing and decreasing as the thermostatic trap opens and closes. An example of a failed thermostatic trap. Bit of a shorter recording, but what we can hear there is clear, visible turbulence, and there's no change in the sound. And for most types of traps, if they fail in the open position, they're going to sound similar. It's that constant level of turbulence with no modulation. So that's our example of a failed thermostatic trap. One of the more common traps that we see in a lot of sites, and a lot of these dotted around, is the thermodynamic disk trap. Now, these again are the on-off type, more commonly used, and operate by pressure changes between steam and condensate. As the condensate builds up, we see the disk move open to allow the condensate through. As the condensate is removed and the steam enters, the pressure changes, force the disc closed and close the trap off. It's quite a harsh environment for the thermodynamic disc trap, where it's constantly opening and closing. And a good one of these would cycle between 2 to 10 times per minute. So we can always then listen as we do it, maybe time it, and we can then get a gauge of how well it is operating. So an example of a good thermodynamic disc trap. So as you can hear there, you hear a steady level of turbulence first of all, then all of a sudden a large rise in turbulence as that steam trap opens, and then you can also hear a very clear abrupt halt to the turbulence as that disc is slammed back down to close the trap up again. So that's how we would see that, and we want to see that 2 to 10 times per minute. And sometimes when we can do sound recordings, that can help us with looking at this too. So a version of a failed thermodynamic disc trap. A high level of turbulence, as we were showing in the previous slides, blowing through, constant steam being flown through the trap, not good. Now, the thermodynamic disc trap has a few signs sometimes that there's a problem occurring and it's on its way out or losing its efficiency. And one of these conditions is also known as chattering. This is where that disc is not seating correctly against the body of the steam trap, and it's no longer able to keep that steam all in there, and it'll start chattering away or starting to expel a small amount of turbulence very frequently. And that's where we can then tell this trap isn't working to its best capability. And this is an example of that chattering. So we can hear that it's in fits and spurts. It's constantly opening and closing, because it cannot make that perfect seal. So because of the harsh environment that it's in, the constant opening and closing, there is going to be damage caused to that disc. So again, being able to compare like for like can help us with getting an idea of the efficiency of these traps. So here's some examples of comparing known states to others. So here's an example of a thermodynamic disc trap again in the field. So as we can see, we see two clear levels of rises in turbulence that shows us the trap is opening and then closing again, and we can see it twice in 20 seconds. So if we then pull that out to a minute, we can see that we're quite clearly within the 2 to 10 times per minute cycles. That tells us that this trap is in a good state. And we can use this with helping us compare, like I say. So here is the next one that we listen to. So as we can hear from this one, and we can see from the time waveform, the numbers of times that this trap is opening and closing is very frequent and goes way outside of the 2 to 10 times per minute cycles. That says the trap is working to an extent, but it's not working to its most efficient capability. So this might be one that we might earmark for future maintenance work on it in the near future if we have any downtime coming up, or something that we will keep a close eye on. To be actually say, right, we're flagging this one up because it's not working to its most efficient state, and we can replace that quite easily, for example, depending on the scenario that we're in. So the next one we're going to look at is the float and thermostatic trap. So this is this is a continuous flow type trap that has a thermostatic vent inside that for airs and gases at the start of build-up. And what we'll have in this instance is that the condensate will build up within the body of the trap, and inside there will be a float, either a free float or a float on an armature that will then rise as the condensate builds up. And as it rises, we'll open the trap further to allow the constant flow and removal of condensate. What we should be hearing inside these when we're listening to the outlet is a steady flow of turbulence, and it may modulate in amplitude as the bore floats up and down as it allows more or less condensate to flow through. What we will also hear inside of some of these traps is the sound of the metallic ball that's floating, and because it's metal on metal floating in a body of condensate, you might hear tapping noises. And with ultrasound, it's very important to distinguish what sound is relevant and which sound is not relevant, so we can ignore this. So in the next sound file I'm going to play now, which is a good steam trap, you may hear the tapping and knocking noises. You want to ignore that and listen to the turbulence behind that to make sure that it's steady and constant. So we can hear that rattling around of the bore float inside. It's a free float trap, and behind that we can hear that turbulence, and it's always there, slightly up and down as we hear it going along. Here is the sound of a failed float of thermostatic. As with all the other failed types of traps, you can hear there the constant flow and sound of steam going through there. Sometimes what we see with some of these traps, that the ball has become damaged or maybe eroded, or there's a hole in it and it's flooded and it stays at the bottom, but we hear no clear sound of any sort of movement from the ball float, and we hear the sound. It sounds almost quite dry as well, if you can describe it, a sound like that. And that's an indication that we have a bad float of thermostatic trap there. So again, I want to show an example of doing some comparison methods here with a good versus bad float and thermostatic trap. So what we can hear here, and what we can see on the time waveform from the sound recording that we have performed, is we can see the opening of the steam trap being a bit wider, pushing more condensate through, but also we can see a bit of the tapping noises from the ball itself. But we can see like a fishtail sort of shape as we hear that turbulence increasing and slightly decreasing and modulating over time. So that's a good example of a good trap. And one that's not so good, we hear absolutely no change in the turbulence. We're seeing no impacting sounds from the float that should be in there, which gives us an indication that this is not good. Even if it was, say, a float on an armature that we may not hear knocking around, what we would expect to see is an increase and decrease of amplitude of sound as the trap goes up and down to open it up a bit more. So this one, clear example of a trap that's blowing through. So as we're performing our steam trap surveys around sites, it is possible to be able to create reports and report on the condition of our traps and actually quantify the sort of costs associated with failing traps or leaking traps that we identify on our survey. And that can be done through the UE Systems Steam Trap application that's free to download on Apple devices only. So onto your iPads or your iPhones. And this will help you in reporting on your steam trap surveys as you go through your site. So with this, there's a few things once we download this onto our device, is making sure at the start that we input the sort of factors, things like the cost that it costs the site to generate 1 ton of steam, for example. Also, the running time of our systems. We might want to set up our leak percentages, because what we would do is that if we identify a leak, well, how much is it leaking by? This is a hard thing to actually quantify. So what I would normally do, my personal opinion, is that I would set anything that's leaking at around 40%, just to keep it on a conservative level. And then when something's blowing through, I don't necessarily put it down as 100% blowing through, but I'll put it at 80%, again, to be on the conservative side of things. As we're doing the inspection, we also need to identify the orifice, the type of trap that we're inspecting, the orifice size within the trap itself, and then we need to make a note of our pipe diameters on the inlet and outlet, for example, and a note of the pressure of the system and our temperatures. Once we do that, as we go along, it's kind of, see it as a notepad, your digital notepad that you're doing as you go along, inputting this, taking pictures of the traps as well. And then once you've completed that, you can then generate a simple report, and it will then be emailed to you, so that by the time you get back to your desk, you would have then a fully itemized Excel spreadsheet reporting on the condition of your traps, whether they're good, whether they're blowing through, or whether they're leaking. And that way you can then get an appreciation for the potential losses that you're facing on your steam traps. And by going around many sites over my time, seeing tagged steam traps that are faulty or blowing through, and you ask them how long they've been there for, and they've been like that for a few years, and they say, well, the steam system's fine. Well, it might be fine, but the energy costs are probably going through the roof because of these faulty traps. So by identifying faulty traps, you can see a return on investment quite quickly if you then implement the repairs that are required on these traps. So yes, ultrasound is fantastic for picking up conditions of steam traps. Now, this is more based around the mechanical based traps. There are limitations sometimes as to what we can identify and how we identify it. And I want to share that sort of information, that sort of limitation with you, so you are aware. And it's something that I've come across in time now, where people have identified something as maybe being faulty, but it actually isn't, because it's the way it's designed and the type of trap it is. And these are the fixed orifice type traps that have no mechanical moving parts. So because they have no mechanical moving parts, it means that actually they are a bit more reliable, because there's less things to go wrong with them. And these operate off a back pressure design, so it allows a continuous flow of condensate through the steam trap itself. And so when you inspect this with ultrasound, it may sound like it's blowing through. And that way, by certain people doing these inspections, you can commonly misdiagnose a trap to be failing when actually it's not. And this is why it's really important to know the type of trap you are inspecting. So I've listened to quite a few of these sort of fixed orifice traps, and it sounds more like a modulation of turbulence, of like blow through almost. So it's understanding, maybe using temperature to help you as well with understanding the condition of these can be useful too. But just remember, if you're looking at a trap that you believe is a fixed orifice and you hear a constant level of turbulence, that does not mean that it is faulty. It's probably doing its job correctly. So that's one way we can help improve the efficiency of our system, by looking at our steam traps. They're the quick, easy ways of doing an inspection to identify these. Another way of looking at helping improve our efficiency is improving our external leaks to atmosphere. We've all seen them. You see your big plumes of condensate and vapor going into the atmosphere, and they've been there for a long time and everything's still working fine. But these leaks are costing you money. These are expensive leaks. So if we can repair these, we can make significant improvements to our efficiency. An example here of a 3mm leak site under 7 bar of pressure, when it's costing the site around £20 per ton of steam, the approximate cost in losses just by one leak alone like this could be around £4,500 a year, depending on variables, of course, but it's expensive. That's the way that we see it. And with ultrasound, because there's turbulence at a leak, we can identify these quite clearly if you can't already see the plumes of vapor coming out already. So a quick question coming in asking, would it be better to check the temperature of the steam side and condensate side to make sure what you find by ultrasound is understandable? Well, yes, that is correct. Thermal imaging and ultrasound do work well hand in hand. Now, say for example, you've just used thermal imaging alone and you see that the condensate is, the outlet side is cooler than the inlet side. That's an indication that steam isn't passing through, but it's also an indication that the trap could be blocked, for example. So we get part of the picture, and that's where using ultrasound alongside the thermal imaging would help us get the bigger picture. So it would almost sort of like enhance what you're doing, and it'll confirm what you're finding. So if you see through a thermal image, you have your cooler outlet, and then you listen and you hear that there's cycling, you know that you've got a good operational trap. So on to the next part. Another one is lagging. Having lagging on your steam pipes, on your systems. I've been to many sites where you walk around, you see all the steam pipes all around the outside, on the outsides of the buildings of the sites and there's not much lagging on them. And having pipe insulation can provide significant energy savings by preventing that heat loss over longer distances, by having some sort of thermal resistance and reducing heat flow from the pipe to the outside atmosphere. This can then relate to our energy savings. As another reason for insulation is the economy side of things. Is a well-insulated pipework system will help cut the running costs and save on maintenance, because we're trying to prevent that cooling effect. And also, steam pipes are going to be extremely hot. So safety is also another paramount to consider when it comes to actually you doing lagging. Also, when it comes to steam traps, but we don't necessarily need to insulate all of our steam traps, because if we lag all of our steam traps, there are certain types that require some sort of cooling to help them in the way they efficiently operate. For example, thermodynamic or thermostatic. If we hold that heat in too much, it might reduce their efficiency in how they operate. So make sure when you're looking at your lagging, look at the type of trap that you're trying to lag, and will that lagging affect its efficiency? So some will, some won't be affected. Think of floating thermostatic that just operate off condensate flow. Having one of those lagged would not cause any insignificant issues with the efficiency of that trap. Whereas a thermostatic that relies on temperature changes in condensate may not operate as efficiently if it's lagged, because you're holding the heat in. So another quick question coming in, can you test steam traps that are used in a vacuum system and also at very low steam pressures? So yes, even though it's at a very low pressure, as the steam trap operates, there's going to be some form of turbulence. And as long as there is turbulence, there will be ultrasound generated. So that's what we're listening for, is that turbulence. And just like you were listening for low pressure external leakage, for example, that still generates ultrasound, generates turbulence, so we can still pick that up. These probes are very sensitive, so you can adjust your sensitivity to listen for lower emissions. So maybe on lower pressure systems, you would have a higher sensitivity. So I hope that answers your question there. So another way we can help improve the efficiency of our steam system is to look at condensate return systems. How do we deal with our waste condensate from our system? Are we disposing it to wastage, or are we recycling that? So condensate itself still holds a lot of heat energy. And by returning that condensate to our boiler feed water, it can help improve our energy usage to the boiler by up to 10 to 20%, because the heat's already in there, so we're not requiring as much energy to return it back to steam. And also, condensate, when it's being disposed of initially, is still technically too hot to be actually disposed direct to sewage. And by having a condensate return would reduce the processes needed to cool it prior to disposal as well. So this is something else to think about too, improving our energy efficiencies. So another thing with steam traps is a steam trap can also be seen as a valve. And of course, we have many valves around our sites. And do we know the condition of them? If we've got one leaking, are we only just finding out because something's at the end of the pipe system that shouldn't be there? And just like testing steam traps, we can test valves. And with the same sort of principle as inspecting a steam trap, we can listen to the turbulent flow from a trap if there's a leak. So if we have a leak at the seat of the valve, we will get turbulence. And what we will do is use a contact method of ultrasound again for listening for that turbulent flow. And the method that we call on for inspecting steam valves is the ABCD method, where we would take 2 readings upstream of the valve, and the distances would be at times the diameter of the pipe away from the valve, and then 2 readings downstream from the valve at the same sort of distances. We can then take a decibel value of each of those points, compare them, and from that comparison, we can determine the condition of that valve. And the rules are quite simple. So we have the ABCD, AB upstream, CD downstream. So if point C is the highest decibel value, the valve is leaking. If the sound from A through to D starts to go down and down and down, the valve is now closed because there is no turbulence being generated. If the values are either the same or extremely similar, the valve is fully open. Even if the valve is slightly open or slightly closed, however you want to see your glass half empty or half full, it will generate turbulence. So you want to understand what state the valve is in when you're inspecting it as well, because having a valve half closed will generate a lot of turbulence. So if we then get to a point where point D, the furthest one down the line, is the highest, the turbulent sound is not coming from the valve. It's coming from somewhere else. And that's where we might start implementing further points like point E further down the stream to listen for where the turbulence is greatest. Because this could be coming from a bend. It could also be coming from a partial blockage. So say, for example, you have a partial blockage in the pipework. Wherever the sound is strongest is where the turbulence is generated, because ultrasound is strongest at its source. So a very easy method for checking valves. And I know that in a classroom activity, having the ABCD method looks great. But let's face it, in the real world, we have lots of bends, lots of turns, access issues, and it might not be possible for us to do this method because you have to be on the pipework. You cannot do it on lagging. You need to be through the lagging onto the pipework itself. So I've done lots of checks on these sort of things where I've just checked one upstream and one downstream, and you can hear the turbulence if it's leaking. We've had people checking on the bodies, listening for the leakage sound. If you've got a leak, you're going to hear turbulence, and that turbulence tells you it's a leak. And ultrasound, what we're picking up in our headsets, is just like audible sound that we would expect to hear audibly. We will hear that sound. So a quick question here regarding the valve passing. Probe will withstand how much temperature when we touch with the probe on the steam pipe. So with the contact module of the probe, it is a sharp point. So the contact surface area of the probe is very, very small. So it can withstand quite a lot of heat at that point because it's not going to transfer that much heat through the actual point of the probe. But you shouldn't need to actually be on the pipework for very long to be able to determine the condition of that valve or that trap. Okay, so you shouldn't need to be on there too long. Some of the probes do come with a magnetic contact module as well, and that one I would not recommend for testing on hot pipework. I would always use the pointed rod, the STM, the contact module for this check. So in conclusion, to these discussions. As we can see, steam systems are great assets at transferring heat energy, but they also require a lot of energy and fuel to keep it running. And if we have poorly maintained systems, it's going to dramatically reduce the efficiency and increase the energy usage on site. If we can perform steam trap inspections to improve our system efficiency, utilizing ultrasound for this method is very simple and effective. And if we then use the reporting tool alongside this, we can help quantify and show how much we can improve our energy savings by making the required maintenance practices to improve our steam traps. So we have a quick question there about how much distance do we keep between points A, B, C, and D? As you saw on the screen there, it was 1 times and 2 times the pipe diameter. So say, for example, you have a 3-inch diameter pipe work. The point B would be 3 inches away from the valve, and point A would be 6 inches away from the valve, for example. Okay, but it's just keeping a uniform distance on each point to make sure that we can do that check. So this is bringing to a conclusion now our webinar today on steam trap inspections. This is our 5th webinar now on ultrasound, and we upload these to our YouTube channel every time we complete them. And we have lots of different discussions where we talk from the simple introduction to ultrasound, to mechanical inspection and lubrication, to electrical inspection, to leak detection or gas leak detection, and also now we'll be uploading the steam one. So there's a whole plethora of information out there for you to access anytime you like. So please feel free to look through those on our YouTube channel. If you have any questions, you're always welcome to get in contact with me, or even look at our website at www.uesystems.com, and there's a learning center on there where you can gain lots of information and lots of case studies and sound files to help you with improving the way you do your inspections. If you have any questions, please feel free to throw them into the chat group now, and I will leave the chat group open for the next few minutes to try and answer some of those questions. And then we will close the webinar, and if I can't answer all of your questions, I will come back to you via email. But please feel free to email me with questions as well if you don't want to ask them in this chat group. But I would like to thank you for your time today and hope that you enjoyed it. So Steam Trap Survey app unavailable on Android. Unfortunately, it's not on Android anywhere at the moment. It's only available on the iPhone devices, Apple devices at the moment. Hopefully that will come out on Android in the near future. Quick question there. Can we use the same kit for foam flow? So the level of turbulence that's generated from different types of medium that's flowing through the pipes will affect the level of turbulence. So things like pressure differences will affect the level of turbulence. The viscosity of the medium traveling through it can affect the turbulence also. Now, depending on the level of viscosity and the level of pressure behind the foam, you may be able to pick this up. You may need to have a little bit more sensitivity on the probe, but it could be possible. So I think we'll bring this to a conclusion, to an end. Please feel free to email me any further questions. You've got my email address up on the screen, chrish@uesystems.com. My contact details are there as well. So please feel free to get onto those if you have any questions. I will answer two more questions I've just got through. How much sensitivity should be maintained to check steam and valve inspections? So when you place it onto the contact surface area, have your sensitivity at maximum to start with, and then bring it down to make it more manageable in your headset. You will be able to be the judge of the sound that you're picking up, that what you can handle safely. Valve inspection using ultrasound, is it done on operational type inspection or shutdown inspection type, or both? There has to be pressure there. There has to be pressure behind the valve to be able to listen to the condition of it. So I would probably say during operational time, which is a great thing because that way you don't have to, it's non-intrusive and you can do the inspection while daily operation is actually occurring. So, okay, thank you for your time today. And I look forward to hearing from you all again. And we'll start playing some more webinars in the near future on some other subjects too. Thanks, guys, and take care.